Hydrogenation. It's one of the earliest organic reactions that you learn after learning about nucleophilic substitution. It involves the simplest addition of molecules to an alkene, or you can also do this to an alkyne. All we add is 2 hydrogen atoms across the double bond of an alkene to give us an alkane, or we could do it twice to an alkyne to give us an alkane. Now it turns out that not only is this simple on paper, but it actually turns out to be a very simple operational experiment in lab. All we need is an active catalyst, which in this case turns out to be palladium metal, dispersed on a carbon support. Now that carbon support is actually just charcoal, and we've taken palladium and just dispersed it so that we get higher surface area, more active catalyst. It's generally dispersed as maybe a 10% by weight or 5% by weight on charcoal. And it's very active, so it's useful for hydrogenation of alkenes, alkynes, reduction of nitro groups to amines, as well as some other applications as well. And it's also tolerant of water, tolerant of alcohols, and so that makes it very useful in many applications. So we'll have some of that catalyst. In terms of hydrogen pressure, we don't need a special apparatus most of the time. We don't need high pressures of hydrogen. Most of the time, all we need is 1 atmosphere of hydrogen, which equates to simply filling up a balloon of hydrogen, purging the atmosphere of our reaction vessel with H2, just to get rid of any air. Hydrogen is lighter than air, and so it's helpful to purge out oxygen and nitrogen from the atmosphere and just kind of fill that, saturate that with H2, and then we can simply let the reaction proceed. All the other things that we need in this reaction is simply the substrate, which in this case what we're going to be using is an alkene from a natural product. This is ethyl cinnamate, and it's found in the essential oil of cinnamon. And we're going to use H2 with palladium and carbon. We'll have a simple solvent here, ethanol. And we're going to hydrogenate this alkene down to the alkane to give us ethyl 3-phenylpropionate, which turns out to be another natural product. It's found in muskmelons and in red fermented soybean curds of all places. And this is also used in the perfume industry. And it's a very simple reaction. So all we'll do is we'll weigh out or measure out our starting material, our substrate, add our solid material, black palladium on carbon, add our solvent, put a balloon of hydrogen over the reaction, let it run for about an hour or so, and then all we have to do is filter to remove the insoluble palladium on carbon. Heat the solution. We'll use a rotary evaporator to remove the solvent, as I'll explain in lab. And then we should be left with simply a clear oil, which we can then take a final mass of and take to the NMR room for final kind of purity analysis. So with that kind of brief introduction to what we're doing, let's head up to lab and set up this very interesting and simple hydrogenation experiment. So here we are in the lab, ready to set up the hydrogenation experiment. The experimental setup is actually very simple. I have a very small round bottom, a 25 milliliter round bottom here, where I will add a stir bar, clean stir bar, and then I'll weigh out and measure out my reagents to add to this. Now, the reagents I've got are the palladium on carbon. I've got a 10% palladium on carbon material. This is solid. I've then got the actual substrate, the ethyl cinnamate, primarily the trans form. So ethyl cinnamate. And then my solvent for the reaction is simply ethyl alcohol or ethanol. Now, whenever you go to set up a reaction, most of the time it's usual and helpful to weigh out your solid materials and add those to the reaction flask first. Then follow that with your liquid materials and solvent. And so here we'll first begin by weighing out the 10 milligrams, or approximately 10 milligrams of the palladium on carbon, the 10% palladium on carbon. We will then add that into the round bottom flask and move into the hood. And then we'll add 100 microliters of ethyl cinnamate, 5 milliliters of ethyl alcohol. And then from there, we'll need to add the active hydrogen source, which is just H2 gas. So I have a balloon here. I'll go fill that with hydrogen gas and then stick that down into the headspace of the round bottom flask. And then get the solution stirring so that it can perform the hydrogenation. So we'll start by weighing out our catalyst. As usual when weighing out a solid, it's helpful to take the piece of filter paper and bend it in half, fold it in half here, so that we have that center crease and so that it will sit kind of upright on the balance. Makes it easier for removal and for pouring the solid later. Tear that. Now I'm ready to weigh out my approximately 10 milligrams of palladium uncarbon. All right, so a little bit over what I need, but 13 milligrams is close enough, and since it's only acting as a catalyst in this case, 13 milligrams is sufficient. We'll take this and add it into our reaction flask now. We've now brought the reaction vial over into the hood to add the liquid reagents. So first I'll clamp my round bottom flask above the stir plate. Ensure that it is roughly centered. And then I'll go ahead and add my liquid reagent, ethyl cinnamate. I need to add 100 microliters with this micropipette. I can then add 5 milliliters of ethyl alcohol. Using a Pasteur pipette. We've measured out approximately 5 milliliters. Using the graduated cylinder, we can add that directly to the round bottom flask. And then the last thing we'll do before we add our hydrogen is that we need to have a septum cap. We'll add to the top of the reaction flask. This will seal the reaction in place. You'll notice I'll need to loosen and remove the round bottom so that I can carefully tighten the wings of the septum cap down around the top. And now you can see here our reaction vial. Now, after I get a balloon of hydrogen, I will be able to add it through the top of the septum with a needle so that it will place this under a hydrogen atmosphere for the reaction. And then we can begin the stirring. So we're all ready to get some hydrogen now. We're here at the hydrogen tank. And I've already turned the tank on by opening this top valve here. You can see the pressure of hydrogen remaining in the tank on this dial right here. And then this dial right here will give me the hydrogen pressure coming out of the tube on this side. Now, I've got two other dials here. I've got a dial right in the middle and a dial on the side. This one simply opens up the valve here to allow gas to flow out of the tube and out of the tank. But this dial here adjusts the pressure coming through that tube, essentially how fast and how much gas is coming through the line. And so if I have this all the way dialed out, then you'll notice that I currently have no pressure. So if I were to open this, I would have essentially nothing coming out of the tube, even though the tank is open. And then, but I can screw this in and adjust it to allow for gas to flow. Generally, I don't need a high gas flow. I'm just filling a balloon. So I may not even register here on the dial. I'm simply going to carefully take my balloon and I'll uncover the one end. Got some electrical tape here to seal it off. I've got the tank open. I'll go ahead and open this side here, the little knob. Have this open. And I can feel maybe just a teeny amount of pressure. I think I need to turn that up a little bit. Oh, there you can hear the hiss. We're getting a little bit of flow. And I've pinched off the balloon. I'll now seal up the end. I've turned off the pressure here. I'll now turn off the tank. And generally, before we would leave, if we weren't going to leave the tank on, which we don't generally want to do, I'd have to bleed off any excess pressure that's just in the line here by closing the tank and then opening this again and bleeding into something. Hydrogen's a pretty reactive gas, and I want to just feed it into the air, but I might feed it into a fume hood or fill up the balloon with the remaining hydrogen pressure that's just in the valves. So there we are. We've got a balloon set for the reaction. So now that we have our balloon of hydrogen, we simply need to add it into our headspace here. So we've got a small gauge needle here. We'll open that up, pull this out. We can then clamp off our hydrogen balloon here so it doesn't leak while we open it up. Ooh, got a little bit of leakage. It's all right. Take the needle, screw it onto the lure lock there, and then carefully remove the sheathing. You can now simply place this down through the septum into the headspace. And then our system should have access to the hydrogen now. We can turn our stirring on. One other thing we need to do to ensure that the atmosphere above the reaction is hydrogen is we should technically purge out the air that's currently above the reaction headspace. We don't necessarily have to do this, but it will certainly speed up the reaction. And so if I take simply another needle, put it down through the septum into the headspace, and push my hydrogen needle kind of down farther into closer to the reaction, and then just let it sit here for a while, just for a little while, purging out the air, filling that headspace with hydrogen. And then in about a minute or so, I'll remove that needle, and then we'll just let the reaction stir. Which should be now all set. Now that the reaction has completed, you'll notice a decrease in the size of the balloon, and we can now remove the balloon, vent it gently into the hood, And we can turn off the stirring and remove the vial from the stir plate. Now set it aside. It looks pretty much the same as we had at the beginning, simply because of the palladium on carbon making everything look kind of black. We will now remove that palladium on carbon by filtering through a kind of powdery substance known as sea light. So to get rid of the palladium on carbon, we're going to filter through a pad of sea light. So here I have the Hirsch funnel. Right here, I'm going to take a small filter paper and add that onto the Hirsch funnel. So a small piece of filter paper there that will keep the sea light in place. I can then take the sea light here and add a scoopful or two directly onto the Hirsch funnel. I'll do quite a bit here just to make sure, really sure that everything kind of gets caught. Pull this off here so you can kind of see. Might be able to see a little bit that pad of sea light there that should catch the palladium and carbon as it travels through. I'll connect this up to the vacuum adapter here. Turn on the water aspirator. All right, so the first thing you notice is that I have a small problem. So I didn't wet the filter paper beforehand, and so some sea light got around the filter paper and down into the collection flask. So this is unfortunate. Probably something I should avoid and make sure that that filter paper is really seated on there well. And so I'll disconnect this and reassemble the apparatus. This time I will rinse with a small amount of ethanol to make sure that my filter paper really adheres to the filter. So now I really should have a good seal between the filter paper and the Hirsch funnel. I'll just wet it just a little bit more just to make sure. Now I should be good to add my sea light without worries of the material going through. We're now all set to filter. So I'll take my round bottom flask that has the material here. We'll open it up, remove the septum, kind of swirl that material and pour it directly onto the sea light pad. I'll then rinse the remaining round bottom with some absolute ethanol. Roll that up, add that onto the sea light pad, and do it one more time. Notice that the stir bar has remained behind, but I could have just allowed it to fall onto the sea light pad and then I would have just collected it later. Last thing is I'm going to rinse the pad of sea light directly. And now once that's done filtering, I should be good to take the filtrate and remove the solvent to leave me with, ideally, my pure product. Now that my solution is done filtering, I will disconnect the water aspirator. And turn it off. I can remove the Hirsch funnel and kind of set this aside. It contains now that pad with the palladium and carbon. And then I've got my solution here, which I want to remove the solvent from to leave me with my product. Now, removing the solvent from this could be achieved by simply heating this on a hot plate, but a more effective manner is to use what's known as a rotary evaporator, also known colloquially as a Rotovap. And to do this, it's more convenient to have your material in a round bottom flask. So I have a new round bottom flask that I've grabbed from the stockroom here, and I have a funnel. I'm simply going to place the funnel on top, filter, or not really filter at all, just simply dump my solution down into the round bottom. And then just to minimize losses due to transfer, I'm simply going to rinse the filter flask with some additional ethanol. And then filter this down through again. Now I'm all set to take this to the rotary evaporator, or the Rotovap, and remove the solvent to leave me with, ideally, my purified product. So here we are at the Rotovap, and I'll sort of go through how we operate one of these. It's different depending on the particular model or style of Rotovap. This one has a water-cooled chiller up here. Many of them have a cold finger that sits in here that would be filled with dry ice and acetone mixture to get it very cold, but here we use simply a water chiller. And the way that this process works is that I have this connected to a water aspirator, such that when I turn the water aspirator on, it will pull a vacuum on the entire system, on this top column, on the solvent collection flask, and then, most importantly, through this center kind of shaft here, through this bulb, it'll pull a vacuum on this, and then finally, we'll pull a vacuum on our actual collection flask, or our flask with material. So here I've got our material here to be rotovapped, or to be have the solvent removed. I'm going to connect that here and then hold it in place with a keck clip. So that snaps in place. Now when I turn the water aspirator on, it will pull a vacuum on the system, pull a vacuum all the way down into the headspace here, which, because the boiling point of a liquid is when its vapor pressure is equal to the atmospheric pressure, well, if I pull a vacuum and reduce the atmospheric pressure, I will get that liquid to boil at a lower temperature. The vapors can then travel up through this column, hit the cold water coils here, the chiller coils, condense back into a liquid, and then drip down and be collected in this kind of solvent trap shown here. Now, I will turn on the water chiller, the chilling water here, which is just sink water, until I have kind of a reasonable flow rate for the chiller water. Not too fast, and you may not be able to see anything at all on the camera, but we have essentially water now flowing through these chiller coils. And then a couple other things before I turn the vacuum on. When I first turn the water aspirator on, it will pull a vacuum, but this valve right here is open to the atmosphere, and so the system won't really be under much vacuum. At first it'll just suck air through here, which you might be able to hear as a hissing or kind of a whining noise. I'm going to close this off here after I've turned on the vacuum, and that will really then allow the system to pull a vacuum. The other advantage with a Rotovap is, you might wonder why such a fancy system. Couldn't we simply pull a vacuum in another way by having it maybe in the filter flask or something along those lines? Well, a Rotovap allows you to do two things. It allows you to turn on the water bath below here, which we can apply heat to the system. Now, how does that work? Well, I have another column here I can turn on, which allows me to do two things. I can lower the flask I want to rotovap into the water bath so that it can be heated. And then also I can rotate and turn the rotation on so that I get even heating and even kind of distribution and stirring while it's evaporating, which significantly helps. And so what this allows is for the system to remove solvent at a much, much faster rate than you would be able to do simply heating on a hot plate in a hood. Plus, you are also able to collect the solvent as opposed to just dispensing it into the air in the hood. And so we'll turn on the water aspirator to pull a vacuum and then lower this into the bath and turn the rotation on. And we'll see it should only take a few minutes to remove the solvent and leave us with a product as a colorless oil. Now that our sample has finished removing the solvent, we can turn off the rotation, raise the flask out of the bath, open the system to vacuum, or open the system to atmosphere really. Turn off the vacuum aspirator or the water aspirator that pulls the vacuum. Turn off the chiller water. Turn off the water heating bath and the column. And now we're set to simply remove the clip and remove our system from the column. It's got some water on the outside, pretty normal. Just sort of dry that off. And what you probably cannot see is that although we've removed all of the solvent, there's still a trace amount of oil here in the bottom of the flask. That should be our product. We'll go to the balance and get a final mass for that, and then prep an NMR sample for NMR analysis to confirm the purity of our product. We'll prep the NMR sample very similarly to how we prepped the previous NMR liquid samples. So we'll take a small glass pipette, dip this down into the oil, make sure that we pull some up by capillary action. We've got a little bit there in the tip. Don't need a lot, but I do have some there in the tip. Then we'll simply place this into the NMR tube. From there, I'll take some NMR solvent. In this case, we are using deuterated acetonitrile rather than deuterated chloroform, but I could use deuterated chloroform as well. And I'll add that down through the pipette to wash the solution down in. Simply then remove the pipette. Cap my NMR solvent, cap the NMR tube, and I'm all set at this point to take the sample to the NMR room for final analysis.